garbage collection going. All right, let me start recording. All right. Uh, okay. So let's start talking about garbage collection. So there are two different kinds of languages that we saw. There is the world where you manage your own memory. And that's the C++ world. And then there is the world where you get garbage collected languages. And this is famously Java, Python, JavaScript, and a bunch of languages, your Rubies and your Perl. Most of the interpreted languages are usually garbage collected. A language like Java is garbage collected. And garbage collection is a very, very important feature of modern programming languages. So today I wanted to talk to you about what it is and what is garbage collection by trying to implement garbage collection in something called, in Lettuce and see how that works, okay? And we'll go through some strategies for garbage collection. All right. So we looked at some examples of memory leaks already, but in a recitation, the TAs went over memory leaks. But let me go ahead and talk about memory leaks. Okay. So this is the number one headache. This is one of the biggest headaches. I won't call it number one, but this is one of the biggest headaches if you are working with C++. Okay. And what is a memory leak? So remember, in a language like C++ or in C, you have ways to allocate new memory, and this is the new operator. And together you have a delete operator. And if you are not careful and you forget to delete memory that you have allocated, then the memory just sticks around. And if you allocate a lot of memory like that, then it is called a memory leak. Okay. And memory leak is a serious performance bug. Who has had experience trying to debug a memory leak, for example, in a C or a C++ program? And tell me over chat, or you can unmute yourself and speak up. What tool did you use to debug your memory leak? All right, so someone's got the right answer right away. Yeah, so the best tool for the job, typically on a Linux environment, is something called Valgrind. Now, of course, one of the main problems with Valgrind, it slows down your program about like 10 to 100%. GDB is a good overall debugger, but I find it really hard to debug memory leaks with GDB. It's very, very difficult to debug memory leaks with GDB. I mean, I don't know of any good feature in GDB that can help you detect memory leaks. What you really have to do is put breakpoints and do all kinds of nonsense. Yep. So Cody has a good point. Using raw pointers is also kind of frowned upon in modern C++. There are some nice pointer abstractions you can instead use with internal reference counts and stuff like that. Well, tomorrow's recitation is, guess what, about smart pointers in C++. So the TAs will talk a little bit about how you can use something called smart pointers and try to unlearn not everything you learned in 2270, but some of the stuff you learned in 2270. Make a start towards unlearning the use of raw pointers. It's completely frowned upon, and you're not supposed to do it these days. And so the students, the TAs will give you a little bit of a tutorial on that tomorrow during the recitation. All right. But memory leaks are seriously hard to debug. Seriously hard to debug. And if you're ever going to write like server code, like code that needs to stay up and run for a long time, and stay alive for a long time. If you have a memory leak, then your code's not going to do that. It's eventually going to run out of memory, and it's going to do something called thrashing, where you're basically not going to have any performance at all. It's simply you need to kill it and restart it, and that happens a lot. Okay, and it's a fact of life, and memory leaks are a serious thing. All right, the idea behind other languages like Java, Python, JavaScript, and so on is they take away from you the delete operator. So there is no more delete operator in these languages. And as a result of having taken away the delete operator from you, it's now the language, or more precisely something called the language's runtime. For Java, the runtime is the JVM. Python runtime or JavaScript, it's the browser's interpreter that's running the JavaScript code, that's interpreting the JavaScript code. So those are the things that are going to have to do garbage collection or memory management. All right, and garbage collection is going to be the main way by which the runtime or the compiler runtime or the interpreter is going to figure out that something, some memory that you've allocated is no longer going to be used, and therefore you can collect it. All right, so today I wanted to talk to you about this under the Lattice language. So we've already done Lattice with implicit refs, and we've already done it with explicit refs as well. It doesn't matter which one we use. I wanted to show you how garbage collection works and how can we garbage collect. And I will start with implicit refs to begin with. But when I talk about a reference counting garbage collector, how we implement it, I will move to the language with explicit refs. Part of this lecture is I'm not going to walk through some code, but I have written some notes for this, which just got done yesterday. And I was doing some proofreading, and thank you for that student, I think Neil, who proofread it a little bit for me. So it would be very useful if you can proofread it. I will try and make some assignments, but right now it might just be some quiz questions that I will post this week, later tomorrow, so that for the next quiz, you will have some questions on memory leaks and reference counting and so on. All right. And those would be questions that will be in the syllabus, but it won't be in the syllabus for your assignments and stuff. All right. Okay. So let's start with a program in Lattice, and let's talk about the notion of garbage. Because if you don't know what garbage is, how are you going to do garbage collection? All right. So we need to talk about the notion of garbage. So let's talk about programs, and let's talk about garbage. All right. Well, it's a good thing we are talking about garbage. So it's good. All right. Let's talk about this. So here is an example program. Let var, and this is in the implicit language. So let me write this like this. Let var z equals 20 in z plus 20, something like that. In why do I write a program like this? I don't know. I just felt like it, right? Let var y equals x plus 10 in something like x plus 1. So here is a program. All right. This is in Lattice, but you can write a very similar program in Scala. So you would say var x in Scala equals, and then within quotes, you would say var z equals 20, z plus 20. And then you say var y equals x plus 10, and then you say x plus 1. So this fragment of code in Scala is exactly the same as what you have written in Lattice. Is that okay? Now, when you execute this fragment of code, what happens is you're first going to look into this part of the let binding. And so you create z, which is going to be a reference to a cell in the store. Okay. Let me know if you're not following what I'm saying and I need to repeat something, but I'm just going to talk about what happens when you execute this. All right. And into that cell, you write 20. All right. And then what happens is you execute through this code. And this expression that I have boxed in yellow right now, the whole thing is going to evaluate to 40. And then what happens here is Z goes out of scope. So there is no more Z. Once you're out of these brackets that I have shown in yellow now, there is no more Z in your environment. It's gone out of scope. And then comes X. Now, what will X get? X will be a reference to a cell in memory, some cell in memory, let's say at address 1. And what value does X get in this program? Let's see if you're following me. 40, very good. Very good. All right. Now what happens? You create Y. So what is Y? So Y is a reference to another cell in the memory. And what happens to Y? So Y gets X plus 10. So it should get, it should point to a cell in which is the value 50, if I'm not mistaken. All right. But then let's focus on this cell here, cell number 0 in the memory. This is an example of a cell that we call garbage. So why is it garbage? So once you understand why this is garbage, you can immediately figure out like what is happening, right? Aha, it is out of scope. So kind of, right? It's not out, the cell itself is not out of scope, because that's a meaningless thing to say that a cell in the memory is out of scope, but it's not accessible from the program, right? So there is nothing pointing to it from the program. There is no ref to it. So essentially, as far as the program is concerned, there is no way I can access the contents of this cell. It might as well not exist, right? So do I need a destructor? That's the question from Lewis, which is a really, really good question, right? But remember, there are two kinds of languages. There are languages where you write destructors because you manage the memory yourself, and that's C++. And there are languages where you do not write destructors. Have you seen a destructor in Scala yet? Have I taught you about destructors for classes? Not yet, right? In fact, there is no destructor, right? So there is nothing there. So what is happening then is some entity in your runtime should come in and say, this is garbage, should identify this is garbage, and maybe recycle it. So you need a way by which when your program is running, your interpreter can make the judgment that this cell 0 is garbage because there is no way to reach this cell. Okay, so Jarek has an interesting question, right? So Gibson, let's talk about two very interesting questions that have come up. So let me start with Jarek's question. Is this why it's declared but uninitialized int and other types in C++ have random garbage values? No. So this is the problem with calling something garbage, right? Because you can call everything garbage, right? Anything you don't like is garbage, right? Anything you do like is not garbage, then that's dinner. Okay, sorry, no, not really, but it's like this term garbage is essentially like thrown around for pretty much everything, right? So the point being that you want to call it something else, right? But you're conflating two things, right? The initialization to some random garbage value is a different notion. This is a notion where you have a cell in the memory that used to be perfectly good, but now what has happened is that cell has gotten lost. You have no way of accessing that cell anymore, and it's just going to lie there and not be used and going to take up 1 unit of memory. Correct. So there's a difference between this initialization to a garbage value, which is different, right? But this is more like saying that a cell is not reachable. Okay, and that is where garbage collection comes in. So it's the meaning, like the meaning of what you call garbage has to be reworded into a more technical term, and we will call this unreachable or inaccessible memory. All right, and so Gibson had a great question just before Jarek's question. How do you tell that there are no references pointing to a cell? And that's the $1,000,000 question, right? That's the question we are going to try and get to an answer today. And there are many schemes for that. And I'm going to be talking about one of those schemes called reference counting, which is a way to tell whether some variable or from somewhere in the program, I still have an in-scope way to access memory. So what does garbage mean? So garbage means that no variable, no identifier in scope points to that cell. Okay. In a second, you're going to see this is not enough. So this definition is a working definition. So I'm going to underline this definition and say this is working definition. And in a minute, you're going to see this working definition is not enough. So for now, a garbage means that no identifier that's in scope currently is pointing to that cell. Therefore, it is garbage. Is that okay? All right. So let me come up with the second, let me try and refine this notion of garbage and show you that this notion of what is not reachable or what is quote unquote garbage for a garbage collector needs a very, very careful definition. And this is why garbage collection gets extremely tricky, extremely interesting. And by the way, there are still bugs in standard language garbage collectors. Like what is the name of the JavaScript engine that Google Chrome runs, the Chrome browser? Do you remember? I think it's called V8, if I'm not mistaken. They found a serious memory leak, like a serious problem with the garbage collector. Yeah, Chromium has a JavaScript interpreter. So it's part of the Chromium. I think it's called V8, but maybe it's wrong. But like 2 years ago or a year and a half ago, they actually found that this garbage collector was broken. And it was broken because of the circular scope that you create when you have a recursion. So if you create a circular scope, it turns out that that scope doesn't get garbage collected. And for some reason, you can write these programs with a circular scope where the closure has like all the variables ever declared in the program, and they will all persist, and the garbage collector won't be able to collect anything because of that bug. Yeah, so it's like yeah, so we are sticking to this meal theme today, but you know, anyways, is this okay? So garbage collectors are very tricky, and I'm going to show you some tricks. Okay, I'm going to show you some tricks. All right. So a question from Sahil. So garbage is anything that is not in the outermost program scope, because in the scope of the inner level, it would still have a reference. Okay, Sahil is starting to understand why this is going to be tricky. So I'm going to have to talk about, like, yes, you have to talk about the inner scope as well. So let me start talking about some examples of things that are not garbage. So let's refine this definition. And let me talk about indirect reachability. So direct versus indirect reachability. And even in a language like letters, this happens. So let me write a program. Let's say let triple pointer. So I'm going to create a very strange triple pointer in the memory. And here is how I'm going to do it. So I'm going to do it in, this is going to be done in the explicit language. And like I said today, I'm going to be jumping between both languages because my memory, my garbage collector, I want it to work for both languages, both explicit and implicit. All right. Yeah, and for example, if there is a memory leak, like Jacob says, a 1.5 terabyte RAM, Mac Pro is still no match for you know, something that's leaky, right? If you and this is a security vulnerability if you have it in a browser, because the JavaScript code comes from some you know, random person who wrote a website in some shady, you know, .com site, which is running on your browser. So it better not cause a memory leak, because if it did, then it's going to shut down everything else for you, right? So all you need to do is visit a web page and your computer needs to be rebooted and you have no idea what happened. And that happens too. All right. So let me create some funky structures in the memory. So here, what I'm going to do is I'm going to write it in the explicit language. So I'm going to say let x equals new ref of 10 in let y equals new ref of x in new ref of y in, let's do something fun with it, dref of dref of dref of triple pointer. All right. So you thought lettuce is too childish, so we can't really do anything with it. But all right. So Logan wants to know about some websites that will cause his computer to crash and have some some stuff there. Well, you know, I am like a really respectable person in a respectable job, so I don't go to websites like that. All right. Let's leave it at that. Okay, so let's look at this program that I just wrote. All right, in this program that I just wrote, can you draw me how the store is going to look like? Right, so what's going to happen is I'm going to first go ahead and create a new ref at 10. So this is going to create 10 at some memory 0. And right now, X is going to point to that. All right. And this is in the language with explicit references, right? And then what's going to happen is Y is going to be new ref of X. So Y is going to point to a memory cell 1, but inside memory cell 1, I'm going to store the value ref 0, so which is going to be a pointer, remember, to memory cell 0. And then new ref of Y creates a memory cell 2. And here I'm going to store a pointer, let's call it ref 1, and let's call it, it points to ref 0. So then I can do, I didn't create a triple pointer. Turns out I was off by 1, which is another standard mistake people in C, C++ make. Let's just strike off one of these drefs. So I could do dref. It turns out to be a double pointer, but you know what? You got a little bit less than you asked for. That's fine. But let's now see what happens to X and Y. So X and Y went out of scope. The only thing that's in scope is triple pointer. So now tell me, are memory cell 0 and memory cell 1, are they garbage? No, right? No, because there are still refs, right? So the point here is this, right? Our previous definition doesn't still work because our previous definition said no identifier in scope points to that cell. And that is true. No identifier that's currently in scope when I'm about to evaluate the dref triple pointer, no identifier that's currently in scope is going to point to this, right? But it's still not garbage. Why is that? Because I have an identifier, triple pointer, that is currently in scope, and it doesn't directly point to the cell 0, but it points indirectly to this cell. Is that okay? So I have to consider indirect reachability. And this is going to be important because in a complicated programming language like Scala or C or C++, I can create complicated data structures like trees or graphs with pointers all over the place. And I now need to say whether something is garbage or something is not garbage. And for a data structure like this, as long as I hold a reference, let's say to root, then the whole data structure is not garbage. The whole data structure is fine, right? So you have to traverse these references, right? So Mikhail makes an excellent point. You have to traverse these references. So all you have is a reference to like a single object here, but then that object may have references to other objects, which may have references to other objects. And you have to follow the chain of references until you can figure out whether something is garbage or not. So for example, if you create a big picture like this in your data structure, in 2270 was all about creating stuff like this in the memory, right? The more complicated, the better, right? As an example, in 2270, you would have called this a DAG, right? And you would have shown this to your friends, and you'd have been like, "That's a hot DAG you have there," right? Something like that. Sorry, really bad joke. I shouldn't try. But you see how this goes, right? You have to go ahead and trace all of this and make sure it's not garbage. All right, is this good? Okay, so Yeah, so this is going to be interesting, right? How are we going to do it today? All right. So then we have to take this definition and we have to say no ID in scope points to that cell either directly or indirectly. So let's modify our definition of what garbage is. So I say, hold on, something is garbage. I think my iPad may have crashed. Okay, so all right, let me just wait a second. Okay, so I say something is garbage if nothing can point to it directly or indirectly. Is that okay? Okay, so let's go on to the next important point, right? So what is the next important point? The next subtlety comes from function calls. All right, so what do function calls do that is so important, right? So remember, function calls can also create references to memory. So let me go ahead, and something has happened to my pen, so give me a second. I'll be back in a second. All right, so let me switch over to a different screen and actually carry on this lecture, right? So function calls are going to be problematic, right? So let's look at some examples where problems arise because of function calls. Yes, so there is going to be two issues that function calls are going to give rise to. One issue is that you are going to have new scopes being created, right? So a function call is going to create a new scope, like stacked frames. You can think of them as stacked frames, or you can think of them as a new scope. So you have to handle function calls. You have to handle that aspect of function calls. There is another aspect of function calls you also have to handle, and this aspect has to do with the closure capture. So what is closure capture or static scoping? So what is that? So here I'm defining a function called foo in my example. Inside foo, I initialize a counter, which is initialized to 0. And then I define my function. In my function, every time you call my function with x, I increment counter by counter plus 1, and I return x plus counter. We saw this example a little bit last time. All right. And interestingly enough, once this definition is done, counter has gone out of scope, right? Or has it? What do you think? So look at the highlighted code. So it's an expression within these open brackets and closed brackets, right? Is counter gone? Well, yes, but you can reconstruct it. No, I mean, it's kind of in this, let's call it limbo, right? It's between being gone and not gone, right? It's like, the spirit has ascended, but it's being held back to the earth by something, right? What is it? Something that's holding back? The closure is holding it back, right? So when you create this function, you're going to do closure capture. Yeah, like if you subscribe to that kind of theology, it's in purgatory, right? But the point is, the counter is still alive, well and alive as far as this function is concerned, but it's now inside this closure. That's a good one, Zach. I'm not going to repeat it, but it's there for everyone to read. All right. So closure capture is another way you can create references. Okay. So it's very, very important that there are many different ways by which programming languages will create references in memory. And if you're a garbage collector, well, not the person who comes and picks up your trash, but if you are like the person who programs garbage collectors, right? You are going to have to pay attention, very, very close attention to every form by which a reference can be created and kept. All right, is this good? So you can now see that there are many different ways by which you can have garbage. And here is the picture after counter has gone out of scope in this program. Here is a picture I have drawn to show you that it's still alive. Well, it's kind of trapped in a closure, but it's still there. So what happens is foo becomes a closure, with formal argument X, the body expression E, which we don't touch, but it captures the environment at the time it's defined. Remember, that's what a closure does, right? And so here you have a counter, a variable called counter, which is referring to your memory cell 0. Can I declare memory cell 0 to be a garbage? I should not, right? If I do, then your program's not going to execute correctly. Okay, and this is the curse of someone who's designing interpreters or writing interpreters, or what makes them earn their salary, right? It's really, really, really subtle. And there are a lot of subtleties I can point out, which is why I did not even attempt to handle this, because this aspect of closure capture is going to be really subtle. You can imagine inside the closure, there is another function called which itself is a closure. So this is like, this is going to be a headache ad infinitum, but you have to handle these. If you don't handle these, then your interpreter will break. It won't work correctly. Is this okay? I hope this is okay. So everyone has a sense of what a garbage collector does for you. Okay, so next time you run a Scala program on the JVM, you should close your eyes and silently thank the poor person who wrote the garbage collector. Just kidding, but it does a lot for you behind the scenes. If you didn't have garbage collector, you can easily write programs even in a simple brain-dead language like letters that will quickly run out of memory. So as an example, I wrote this Fibonacci program. And this is basically the recursion for Fibonacci. You can see here, it's what you would expect. It's a function. It's defined through letrec, where if x is less than equal to 2, then it returns 1. Otherwise, I just put in a var. Why not, right? Suppose, you could have done that at the beginning of the semester, fresh from your previous data structures class, where you have all been drilled into the importance of side effects and living a very side effect filled life, right? Whatever that means. You would have said, I don't like these vowels. These vowels sound like they are where what you would get when you program with your hands tied behind your back and you have to type with the tip of your nose to write the program. That's exactly what programming with val is, right? So I'll write a var. So I slipped in a var here. So I just said z is Fibonacci x minus 1, and I'm going to assign to z plus Fibonacci x minus 2 and return z. All right. With all of these, you can actually see that every time you call Fibonacci, it's creating a new cell in the memory called z, which is being pointed to by z. But as soon as you're done with the current iteration of Fibonacci, that goes out of scope. You don't need that z anymore. So you're going to create as many cells in your memory as the number of calls to Fibonacci 20, which we have already established is like a humongous number already. So eventually, like Fibonacci 30 or 40, in a very simple program like this is already going to bust your the amount of memory you may have in your computer. Okay, so Mikhail has a question. Are garbage collectors much less efficient than managing memory yourself? Well, we are going to answer that question, right? Are garbage collectors much less efficient than managing memory yourself? You have to define efficiency, and let's talk about that. Because, for example, a memory leak is going to kill your efficiency. Because what happens in computer systems is if you allocate too much memory, then you're going to have this bad thing that's going to happen called a page fault. All right. When you have page faults, then your computer is going to take memory from the disk and bring it back to your main memory. And if you have a lot of page faults because you have a memory leak and you're just gobbling up memory like there is no tomorrow, your processor just slows down. Your program's going to slow down completely. So you won't get any performance, right? So you can talk efficiency all you want, but at the end of the day, if you have a bad memory leak, your program's not going to be efficient. All right. So Cody has another question. Part of the issue with garbage collection is you can't predict when the garbage collector might run, which is a really good point. I'm going to talk about that. All right. So I'm going to talk about two different styles. And in one of the styles, you can predict, and in another style, you can't predict. All right. And I'll talk about both styles of garbage collection. All right. So, and the kind you're talking about, Cody, is called a mark and sweep kind of garbage collector, which is different from a different kind of garbage collector called a reference counting garbage collector. Now, of course, there are different like trade-offs people make and things that are in between, which can work either way. Anyway, is this all clear? Notion of garbage. All right. So this is the example with indirect reachability. This is the example of reaching through closures. So you have a lot to think about. All right. So now let me talk about how garbage collection is going to get implemented. Okay. And the most important thing is we are going to change the way the store is going to be managed. All right. So let me talk about how the store is going to be managed. And I'm going to be talking about a special kind of garbage collector called a reference counting garbage collector. There is a different kind called a mark and sweep garbage collector, but that I'm not going to be talking about today. I'll give you some places where you can look that up. Okay, and that's different languages implement different types of garbage collector. For example, CPython, which is an implementation of the Python interpreter, uses reference counting, uses this solution that I'm going to be talking about. Whereas smart pointers, which you're going to be talking about in the recitation tonight and tomorrow, is going to be using reference counting. On the other hand, Java uses something called mark and sweep, where the garbage collector will run periodically. All right. So in a reference counting garbage collector, what we are going to do is every object in the memory or every cell in the memory is going to carry with it an extra bit of information. Well, it's more than a bit. It's going to be an integer that's called the reference count. All right. And we are going to track as the program runs, how many references are there from the program to cell number 0? How many references are there from the program to cell number 1? How many references are there to cell number 2, 3, 4, and so on? In this snapshot that I provided in this little example, you can see that cell number 1 has reference count 0 and cell number 4 has reference count 0, which means that these cells are no longer reachable and therefore they are garbage. All right. And because these cells are garbage, what this means is the next time your allocator is being asked for new memory, it can recycle one. It can swap out what is here, put in a new value, and give it back to your program as if it's fresh memory. Okay, so that's what garbage collector does. It has to recycle memory. There is a different kind called compacting garbage collector. In a compacting garbage collector, what that would do is it would try and move cells 2 and 3 up so that all the memory allocation is contiguous and the garbage is always at the end. Okay, so that's called compacting. So you can do a compacting garbage collector versus a non-compacting garbage collector and so on. With reference counting, the most natural scheme is to basically say when you don't have a reference to a memory cell, that memory cell is garbage, so it can be recycled. So the next time I call a new ref, I will get to this and I will give you back cell number 1. Is that good? Aha. So Emma has a question. Is there an advantage to compacting versus non-compacting? Well, the nice thing about compacting garbage collector is it reduces something called fragmentation. Okay. So hopefully you take a class in operating systems. I mean, I'm hoping that in systems they taught you a little bit about, if you have taken it already, they taught you a little bit about fragmentation of memory. So if you have a large amount of memory, but you've allocated like little like spots here and there, you might have a request for memory that comes in and it says, give me like 500, give me 500 kilobytes of memory. You might have 500 kilobytes, but you might not have it in one place. You might have like 20 kilobytes in one place, 30 kilobytes in another place, 70 kilobytes in a third place, right? And together they add up to more than 500, but you don't have like one chunk of memory that's free, that's total 500, all right? And so that's called fragmentation. And what happens in a compacting garbage collector is it tries to reduce fragmentation as much as you can. So yeah, so so Logan has a point that what if you allocate more memory space, but you may not use all of it? Well, that's not fragmentation. So we assume that whatever the programmer has requested is being completely used, so that we don't look in behind the shoulder of the programmer and says, hey, this is what we need to do and that's what we need to do. Okay, looks like there is something called the malloc lab, right, where you do think about these things. Is that right, Sean? All right. Yeah, but that's a very important idea. And sometimes, it happens to your disk as well. Um, there's something called defragging your disk. I don't know if you ever need to do it these days. I don't think you need to do it with the Mac. Um, but there is something called defragging your disk sometimes. In Windows, you definitely do it. It's a very important idea in systems where if you have memory, that could be disk memory or RAM memory, right? You have to think about fragmentation, and compacting garbage collectors actually talk about fragmentations. You're right. Modern hard disks don't need defrag, but previously when I was, when I was a student like you, my computer used to need defrag, and it would run really fast after defrag, right? So that's an example of what a compacting garbage collector tries to achieve. It tries to do defrag, but we are not going to do that. We are just going to look at garbage, and if a new request comes in, we'll allocate store cell number 1. If another new request comes in, we'll allocate cell number 4. Okay, so the point is, these reference counts already tell you what is garbage and what is not. Any questions so far with reference counting? All right, so if that is clear, let me talk about how do we do reference counting? How do we implement a store with reference counting? And how do we then tie it with the interpreter? So there are 2 steps now. All right, hopefully my pen is working now. Yes, it is. So let's go back to my notebook on my iPad, and let me try and write a little bit more. Okay. Hopefully you're following with me. You're following what I'm saying so far. So let me talk about, reference counting. Store. You know the idea already. So it's going to be now a store with 2 things, the value that's being stored in a cell and the ref count of that cell. Okay, now tell me, what are the operations we need to support? So we need to support allocate new cell, right? So you need to allocate a new cell. How do you do that? Very simple. You're going to go and scan the memory, and you're going to end up at the first point where your reference count is 0. So you get to the first point where your reference count is 0. And now you can recycle this cell and reuse this cell. All right, so allocation is going to be different now. So instead of just allocating tacking on a new cell at the end, so instead of having a new cell at the end of the memory like we did before, now allocation is going to search until you get to a point which has no reference count, and you're just going to allocate that cell. Is that okay? So that's one operation. The second operation is, and here is an interesting operation. Deref is going to be the same as before. So deref a cell in the memory is going to be the same. You're just going to look up that cell. You better not get a request to deref a cell with the reference count of 0. Any cell you deref, the reference count better be positive. Otherwise, your garbage collector is seriously broken, right? But hopefully you're derefing only cells whose reference counts are positive. Last but not least, you can do assign ref. So assign ref to a cell a new value. Is that okay? So you can assign ref to a cell a new value. Now put on your garbage collector hat and tell me, if I had a cell in the memory, which had some old value, and let's say its reference count was 2, and I swap this old value with a new value. So I swap this old value with a new value. Do I need to change the reference count? No. Okay. Is that okay? I don't need to change the reference count, right? Of that cell. Is there any situation you can imagine? And now, yeah, so no, Logan's answer is correct. I accept no. Can you imagine any situation where you have to change the reference count of some other cell? Now, this is where reference counting gets very, very subtle. So suppose, remember, I used to have old value in this cell, and I have replaced it with new value because I'm doing an assign, right? What will can you imagine a situation where you have to change reference counts of some other cell in the memory? Aha. So Emma has a really good point, right? So it turns out you do, right? Even operations like this become very subtle. Exactly, right? It would be like our example with the triple pointer. So let me give you an example. Suppose in my store, I had a reference to like a number, sorry, just a number of 20, right? And let's say its reference count was 3. Let's say its old reference count was 3. And now suppose the programmer, for some reason or another, swapped in this number with, let's say, a reference to a new cell, 40. So now instead of a number, the programmer has put in a pointer in that cell. So what you should do is then go to the memory address 40, and you should increment its reference count by +1. Now, if that memory address 40 was, let's say, a reference to 30, then go to 30 and do a +1, right? Recursively, you will come up with like a chain of +1s, right? Because you introduced a new reference here, you have to go ahead and increment all the reference counts of everything that's reachable. On the flip side, for example, suppose your old value was reference 40, and your programmer changed that into a new value, which is, let's say, number, the new value was number 10. Well, now you have to go ahead and decrement all these references because a reference used to exist and now it's no longer exists. So remember, this assign is not trivial anymore. You still have to make sure that your reference counts remain consistent when you do this. Is that okay? So you have to now implement these operations carefully in your store. The interface for the store must implement these operations carefully. Is that okay? So you have to maintain the reference count as things change, and you have to keep the reference counts consistent. All right. Here is another example. Another operation we'll have to support. We'll have to support an operation called increment reference to a cell. So increment the reference count to a cell. And then another operation called decrement a reference count to a cell. And these are operations I'm going to use in a second. So increment reference count to a cell, what does it do? So suppose I have a store, and I have a cell, let's say cell number 20, and I call increment reference count to cell number 20. And let's say the old reference count was 2, then the new reference count becomes 3. Is that okay? Okay, so there seems to be questions. I will answer them in a second, but let's focus on this increment reference count, then I'll get back to questions. All right, so when I do increment reference count, then I increment the reference count by 1, 3. Now the point is, if this cell itself points to some other cell, then I have to go to that cell, whatever cell that was, let's say 10, and I have to do a +1 on that. Now if that points to some other cell, then I have to go there, and I have to do a +1 there until I get to an end terminal point where I have either a number or I have a Boolean. Okay, in those cases, I can just stop. But remember, when I try to increment the reference count of one cell, I might have a chain of increments that go all the way around. Okay, so let's answer some questions. So John's question is like we did in our recent example with triple pointers. Exactly, right? You can have internal references from one cell to another. Okay, so then the next question from John is, suppose you have a doubly linked list where you can go back and forth between the refs. Does the reference count increase for that? Aha. So here's the point. Reference counting is not going to work if you have cyclic references. So the idea here is you're not allowed to have cyclic references, like a reference from A to B and a reference back from B to A. What I do in my implementation is I do a depth first search. So I implement an algorithm called depth first search, and I keep a list or a set of all the cells I have visited so far, so that I am not trapped in a cycle and do an infinite loop forever. So you can get rid of that. But the problem with this is when you have a cyclic reference like this, B is going to refer to A. So A's reference count is always going to be 1 because B is pointing to it. And A is going to refer to B. So B's reference count is always 1. So these are never going to be garbage collected. All right, so if you have circular references, then reference counting does not work. The only thing I can do is in this process of incrementing references, I can make sure that I never get into an infinite loop. And if you read my code, it is there in my code. Okay. And can you create examples like this in Lettuce? For sure, right? So you can always create an example by saying let x equals new ref of 10, and then I can say let y equals new ref of 20. And then I can just try and do assign ref xy, and then I can do assign ref yx. So if I tried something like this, I might need a temp. Yeah, I might need a temp. But you can always do this. You can. There is a way by which you can always create circular pointers, right? So I guess you'll have to do something like let temp equals. You can fill out the details. Let temp equals x in, assign ref x y, assign ref y, and this should be temp. You can do this, and you will create two references that are circular in the language Lettuce. You can do that in the explicit language, and reference counting will not work for circular references. Yes, so John's point is exactly right. This is why we should try not to use circular pointers if at all possible. Though Java's implementation is something else, it's called mark and sweep, and that is not fooled by these kinds of circular references. So if you go and look up something called mark and sweep garbage collector, that is not going to be fooled by circular references. But this reference counting, as you rightly noted, is going to be circular references are going to kill it. Tomorrow, when the TAs talk to you about smart pointers, they will talk to you about a very special kind of pointer called a weak pointer, and that's what you should use for doubly linked list in C++ if you're going to use smart pointers. But that gets too deep into the weeds for this. But is this okay for reference counting? All right. So now I have shown you one part, like a glimpse of one part where I have shown you how to implement a store with reference count. Now that needs to go hand in glove with the interpreter, which needs to manage the references. So what's the idea here? So the idea here is I'm going to have to change the way I write my interpreter to track reference counts. So I need to change the interpreter. So I need to change the Lettuce interpreter to track reference counts or to track update reference counts. How? Okay, so I am going to, for sanity's sake, I'm going to not consider functions. And you already saw functions create their own kind of problems because they are going to create a new scope whenever you call a function. And they are going to create closures which are going to hold references inside them. And that's just getting started. There is one more problem. There is a very particular kind of hell reserved for those who like Caret functions. because curried functions are going to be problematic as well. Let me just say that and not get into the weeds here. Okay, seeing that curried functions are problematic is something I realized just yesterday night. All right. I didn't realize that curried functions would be problematic, but they are problematic with respect to garbage collection. So you have to do some special things with curried functions. And I'm not going to go that deep into the weeds. So I'm going to throw away these things. And I'm simply going to consider in our language, we are going to have our explicit ref language. We can also do it for implicit references. In fact, it's easier for implicit references. All right. Yes, so Emma has a good point. Am I going to throw them in the garbage? No. The point here is this. If you want a complete working garbage collector for letters, you really have to do function calls, right? I'm taking your question a little bit seriously here. I know it's meant as a joke, but you do have to deal with this. As someone, if you're ever interested in designing your language, or if you're ever interested in, let's say, building some kind of a garbage collected domain-specific language implementation in C++, let's say for some library you're building, you do not have the luxury of saying, I will deal with that tomorrow, right? You have to somehow come up with you have to come up with some way of handling everything, or you have done nothing, right? But today I'm a professor, and this is Lettuce. It's not a serious language that you're going to use in the industry. And so we can play loose with some of these things, right? But in the real world, you have to really do some work. And by the way, Zach and Jacob had a question, which is, when you try and chase these circular pointers, would we keep incrementing forever? Not really. If you read my implementation in my notes, I try and detect cycles, and I try and not keep incrementing in an infinite loop for cycles. But you still cannot garbage collect cycles. If you have cycles in the memory, a reference counting implementation will not be able to garbage collect. Okay, very good. So let me talk about how do we manage this, right? And the secret here is just, it reduces to one thing: let bindings. So here's what happens. When I do let x equals E1 in E2, all right, what am I going to do is this. When I have finished evaluating E1, so suppose I finished evaluating E1, then I create, in my environment, I create X, and it is bound to the value V1. Now, if V1 happens to be a reference to a cell in the memory, then at this point, my interpreter is going to increment the reference count to this cell J. And then at this point, after E2 is done evaluating, I'm going to decrement the reference count to that cell J. If I make sure that in every let binding, I do that, right? If the let binding assigns to X a reference to a cell in the memory, then I increment, after I'm done processing the E1 part, I increment the reference count to J. And when the let binding is finished, I decrement the reference to J. And this, along with and if I'm doing the implicit reference language, if I'm doing the implicit language, I have to do the same for let, and I have to do exactly the same for let var. Okay, is that okay? That's it, right? So if you don't have functions, and if you don't have closures, this is enough. With all the things going on in your store, this is enough for reference counting in our language. All you are doing is you are simply taking care of any time a new identifier comes in scope and gets bound to some reference, you just take care of it. Everything else gets taken care of by the implementation that I have done already in the store. So since the store itself keeps track of internal references from one cell to another cell, and takes care of all of that, this basically is it, right? This is all you need to do to have reference counting. Of course, in the absence of functions. So in the absence of functions. In the presence of functions, I can say what is going to happen, but I'm not going to fully implement these things. In the presence of functions, what's going to happen is, first of all, you might have something like this. Let foo equals function of x e in. So now, instead of foo being assigned to a reference, foo will be assigned to a closure. And this closure is going to have x, e, and it's going to have an environment. So whenever I have closure, I need to go look inside this environment. And if there are references here, I need to collect them. I need to increment their count. So anytime a closure gets created, I need to do a reference count incrementation. Okay, and that's going to be super important. Okay. Likewise, if I have a simple function call foo of x, this x could be a reference to a cell in the memory. And then this is going to call the body of the function. And here I'm going to create a new reference to that cell. So new references happens. So I need to increment the reference count. But when the function finishes executing, so when I exit finishing the function, I need to decrement the reference count. Okay, so there are going to be some very interesting ways by which I have to know when to increment the reference count of which reference and when to decrement the reference count. And if I do that properly, and I can guarantee that for every cell in the memory, the reference count accurately counts how many references exist from the environment of the program, broadly defined, to that cell, then I can guarantee that this is all correct and this all works. And it's a pain to get this completely correct. All right, it's going to be a really difficult task, but if you can carefully take care of all these cases, then you are fine. Then you got your reference counts fine and everything will be good. Good so far? All right, so I hope this is good. And so the nice thing about reference counting is this. It works hand in glove with the interpreter. As you're executing various parts of the program, you are incrementing and decrementing references, and somehow there is no, like, it's almost like there is no separate garbage collector. It's like every operation you do, there is a little bit of garbage collecting going on because you're updating the references. So that's the nice thing about it, right? It's really good. And even in a language like C++, you can build reference counting for the objects you create. So this is a nice, easy or easier algorithm that as a developer, you can add it on top of C++, and you don't need to do it because there is already a library that does it called the smart pointers in C++. They already implement reference counting. So this part is great, right? So it's a simpler solution than the alternative, which is this mark and sweep kind of garbage collector, and it has some good advantages. What are the disadvantages of reference counting? What are the disadvantages? There are many. Let me start with the simplest one. Suppose you have a big tree in your memory. So suppose you have a huge tree in your memory. Okay, this is a huge tree, and you just have this innocent little pointer to the root of the tree. All right, and let's say you're doing reference counting. All right, and let's say you made a copy and you said root 1 equals root. So now you created a new reference called root 1, which is a reference to the root of your tree. I mean, this is supposedly really innocent, right? But what happens here is the reference count of this cell increases by +1. And then the reference count of the cell below is +1, +1, +1, +1. So you have to go through the entire tree, traverse the entire tree, and make sure that all reference counts are updated in the tree. Otherwise, you are going to be in trouble. Okay, so this is number one. And if it's not a tree and if it's a DAG, then you're going to have all these pointers like back to each other. Even though you don't have a cycle, you're going to again have to do a lot of work. So even like a simple assignment operator or a copy operator of a pointer in your program can trigger a huge reference counting update, right? And then suppose root goes out of scope after this, then all the references will have to come back down by -1. Okay, so there is a lot of extra work that goes on. And the question is why, right? Why do you need to do all this extra work? Sometimes you don't need to do all this extra work, right? So sometimes when you have pointers to large objects, when you have pointers to huge objects in the memory, in smart pointer, you will learn tomorrow, you would use something called a unique pointer. And in unique pointer, what you will do is you will always guarantee that there is just one pointer here to the root, and no other pointer is allowed to point to this object. And what you will see is when you do that, you can do away with reference counting, because at any point, you only have one place in the program from which you can access that object, and you will never keep copies of that pointer. And when you do that, it's called a unique pointer. You will see that tomorrow. And that saves a lot of performance overhead when you have huge objects in the memory, because then every little pointer operation, like you touch the pointer here, then you trigger a huge reference count change. And then you touch the pointer there, then you trigger a huge reference count change. That's going to be bad for performance. Is that okay? Number one. Number two, of course, reference counts are not going to be cheap, right? For every object you create, there has to be an extra little bit of memory tucked away somewhere where you need to put its reference count, right? That's going to be a problem. If you're going to have a lot of little objects in the memory, then you have to have a lot of reference counts for these little objects. And at some point, it's going to be problematic, because you're going to double the memory overhead or increase the memory overhead substantially. That's point number two. Point number three is when you have multiprocessor environments. And I'm willing to bet a significant number of you today are joining this class on your laptop, and your laptop already has multiple CPUs with multiple caches. Okay, so there is a lot of concurrency that goes on. And the problem with reference counts is that if you have concurrent systems with multiple threads of execution on multiple CPUs, maintaining these reference counting operations is a pain, because all of these operations have to be what are called atomic operations. So all of these have to be done atomically. If you have your local cache, then your local processor cache gets invalidated. You have to do cache synchronization. Then you have to do something called memory fences, because modern memory systems, modern RAMs don't do sequential write. So if I told you to write to address 1, then write to address 2, then write to address 3, they may reorder, your memory system may reorder the commands like read and writes as it will. And it's called weak ordering or weak memory consistency. And if you have those kinds of things, you have to implement something called a memory fence. This becomes a mess, a real mess. Okay, so garbage collection is a real mess, and you don't want to be messy when you're collecting garbage, right? All right. So these are some of the problems, right? And last one is the circular references are not going to get garbage collected. And you better deal with it. So if you're going to implement a doubly linked list in your language, you better figure out a nice way of implementing it that's still going to sit well with your garbage collector, because otherwise it's not going to get garbage collected. And this happens a lot in Python. You can easily fool the Python's garbage collector because it just throws up its hands when it finds a circular reference. It's not going to garbage collect it. At least the C Python implementation is not going to garbage collect it. Okay, so these are some of the problems with garbage collectors, right? On the other hand, like I said, if you had a memory leak in your program, which is serious, then forget it, right? There is no way you can get your program to be performant. Okay, and a lot of programs that we write at this stage in our education tend to be like simple programs, which are not going to stick around for too long, which are not going to generate a lot of memory references in the first place, so you're not too worried about it. Eventually, when you go to the industry and you start writing complicated looking programs, you are going to create a lot of garbage, right? And so you better need either a good memory management strategy, you need good programming skills to manage the memory yourself, or you need to use something that manages it for you, or use something like a smart pointer, which would be somewhere in the middle. It gives you some control, but it does some management for you, it gives you some control, but ultimately you are the person responsible. And if you misuse it, you won't even know what hit you. All right, so that was my cheerful way to end this lecture on garbage collection. So hopefully lots of food for thought. Do attend the recitation on smart pointers. If you're ever going to be a C++ programmer for a good company like Google, for example, and you want to keep your job, then you will learn what a smart pointer is. So you can get a little bit of an idea tomorrow, and hopefully next time you ever have to program in C++, then you can use smart pointers. Okay, any last questions before I finish today's lecture? Okay, I hope you enjoyed the lecture, and thank you, and I'll see you around. Do look up the other kinds of garbage collectors, and do read a little bit about different languages garbage collectors. It will be very informative. You can definitely impress your colleagues in the future when you're in a company or when you're in a research group. Yeah, be knowledgeable about these things. Okay, see you. Thanks.